Okay, so will we start? Shall we start? Okay, so good morning, everyone, and welcome to this. Something is recording, right? Yeah. So, welcome to this third workshop on MicroSim. This, as you know, we have had two workshops already, and this is the third in the series. And essentially, this purpose of this workshop is essentially to go through the updates that have happened in the last year, and also to come off with a new release at the end of it. So, as the team involves professors from IISc, IIT Bombay, IIT Hyderabad, IIT Madras, CDAT Pune, and Savitribai Phule Pune University, and this project is funded by the National Supercomputing Mission. So, this is our team of developers that are listed over here, which includes PhD students, postdocs, bachelor students, and also internship students who have all contributed to the parts of the software that you're going to see today. So I will just give, this might be a little bit old for the people who have already attended it, but there's maybe some new people, so I will just repeat it quickly. The reason our work is relevant is because of the broad scheme of the materials phenomena that spans the complete length and time scales. And as you see, if you were to describe the structure of matter at the different length and time scales, we will essentially see a wide variation. And therefore, classically, if you were to understand the phenomena using experimental techniques, you would use experimental techniques at each scale and try to understand the phenomena at that particular scale. So complementing this, you can also do it with materials modeling, and where you can essentially write down models relevant at each scale and then perform scale bridging approaches such that you can take information from models downstairs upwards or upwards down from the larger length scale downwards, and combine them in a way that you can essentially get some comprehensive idea of what is happening to the material. Now, if you look at the models at the different scales, you have models at the electronic scale, for example, DFT, models at the macroscopic scale, which are finite element based and Fourier transform based, and then you have mesoscopic models, which essentially look at the grain and the defect structure at the scalar dislocations. So, if you were to make a nice chart about this of the relevant models, you have models spanning all the way from atomistic to the continuum, and essentially one of the challenges over here that we faced is that if you look at the electronic structure, molecular dynamics, even finite element, you have a lot of softwares already available in the market, and that allows people who are entering that research activity to start off without too much of a problem. Whereas if you were to look at the mesoscopic scale, which is essentially including phase field, dislocation dynamics, and on it Monte Carlo, even thermochemical models, which essentially interface between the continuum and the electronic scale or the molecular dynamic scale, the softwares available are either rudimentary or are not usable straight off the market. So here is where the motivation for the development that we are going to be talking about today came about. So that's where MicroSim originates. And essentially, this is the state of the affairs with respect to the softwares available. I have listed down the softwares available at each scale, and you do have my mesoscopic simulation packages like Micros, OpenFace, Space 3D, Prisms PF, and Provos. But what I'll show today is that there is still the softwares could be more flexible, and that is the essential motivation for our work over here. So a basic intro into what the phase field model is. It's essentially you start from a functional, and this is just a representation of a functional which has different parts, and the two basic parts which are typically common to all functionals will be of the terms which are radiant energy and the potential energy, and that you will have some thermodynamic driving force driving the system in the direction which the phase transformation or some other transition is going to happen. And there are relevant material parameters determining the surface tension, and the thermodynamics that enter the functional description, and thereby you can model realistic phenomena. Now, the phase field is a model of choice for that particular scale, is precisely because what it can do, it can essentially be utilized for range of phase transformation problems, solidification being one of them, precipitation being another. As you see over here, here in the top part you have three-phase solidification of eutectic, which is essentially solidifying towards you in a directional solidification setting, and the phase field microstructure evolution is able to show you that the simulation can predict microstructure formation and pattern evolution as the experiment is progressing. Now, this is very powerful in the sense that the typical question in an experimental setting is, if you were to start off in a particular process parameter setting in an experiment, what is the microstructure that evolves? This is a basic question that any microstructural engineer will be worried about, and anybody who is wanting to do any materials engineering will be worried about, and therefore phase field feeds into that particular activity quite seamlessly. Similarly, the same question at a different scale of precipitation is happening downstairs, where you are essentially modeling coarsening phenomena, and that itself, as you see, the precipitate distribution and size evolves as a function of time, which can be captured using phase field models. So the relevant problem that phase field directly attacks is precisely phase transformation problems and relating the process and the structure that evolves. But this is not limited to just the phase transformations. You can also do problems where interfaces move. So this problem that you see in the middle top row over here, it's essentially something related to defect formation. So you have essentially migration of material in response to electronic current that is driving the material from one end to the other, causing voiding in the material. Now, this is relevant for problems where you have very large electric currents, for example, in your interconnects that are used in your circuits, and therefore the breadth of problems that the phase field model can address is pretty large. Similarly, it can also do multiphysics problems of this type, where you are essentially having domain formation in ferroelectric materials, which is again one of the classical problems in materials physics, where you want to control these domain structures for property. So the middle picture over here is the classical dendritic solidification, which is one of the oldest applications of the phase field metal. But this is utilization of a phase field model for a real alloy, and that's what makes it also powerful. That it's not just for model systems, but you can actually couple with thermodynamic databases and model these systems. So the message that I wanted to give from this slide is that phase field is a technique with a flexible range of applications, and therefore it is the relevant choice of model for that particular scale, and that's why we chose the phase field model. So, giving a broad idea of what MicroSim, the structure of MicroSim is. So it has, this is essentially what it offers to you. It first offers to you models that give you a different choice of different modeling frameworks. So, for example, we have the grand potential model, the Kim-Suzuki, the orientation field model, and the Kahn-Hilliard model, all packaged into one, and which is typically something you will not have in most packages that are openly available. Okay. Along with that, we have tried to couple different discretization strategies. So you have the finite difference, the fast Fourier transform, and the finite volume based strategies. And again, this is something which is not offered by people in the broad computer community. Going further, you have flexibility to choose hardware, and this becomes very important in the context of the national supercomputing machines that come up that have come up in India, and also the hardware that is available to anybody who is pursuing computing. Typically, you have some something that is available to you at a given amount of time, given point of time, and you would like to essentially launch your software in that using that hardware. And this flexibility that we have provided in the software allows you to do that. All right. And one of the most important things that actually makes this solver usable, particularly to the industrial community, is the coupling with the CalFAT databases. And this was a non-trivial task in the sense that ours is an open source software, and it needs to talk to commercial databases which are proprietary. So we need to have a mechanism where we are able to extract information in appropriate fashion and utilize the information into our software such that we can do realistic simulations. And this is something that we have incorporated into our open source software. We have a graphic user interface for initializing and getting our initial solvers ready. And this allows anybody who is entering the phase field method as a starting point to seamlessly enter, as there is a lot of help in creating the infile, which is a distinguishing factor from many softwares. For example, if you were to just look at LAMPS, you just have an infile with a lot of description in the manual, but a not one-to-one interface that you directly start with. So this graphical user interface allows you to do that. And finally, we have a post-processing tool. So you just don't simulate. You actually can find out metrics of your, you can calculate metrics of your microstructures, which are relevant for any property predictions that you would like to make, as well as any post-processing that you would like to do beyond the phase transformation that you simulated. So that's essentially the structure of MicroSim, and that's the a brief input about how we couple to the thermodynamic databases. So as I said, you have encrypted databases and unencrypted databases. So encrypted databases come from two proprietary developers, Thermocalc and Pandat, and you essentially have APIs to extract information. That's what we utilize to have the input for our phase field method, which directly goes into the MicroSim software. For unencrypted databases, we utilize Symbolic Python and PyCalFat, which is an open source thermodynamic software. And we have utilized these to write our Python file, which essentially extracts the informations of the free energies in a symbolic fashion. So essentially, the text files containing the TDBs get converted into free energy functions, which can directly be utilized into the as input into the phase field solver. So this is a much easier comparison, methodology in comparison to the other one. However, both exist in our software. Okay, so I will briefly go into what the solver does for you, and this is possibly best done by a demonstration. So I will briefly demonstrate very simply what we are going to do, and that will also take you to the updates in the present thing that we have in the present release. So this might not be visible to you directly, so let me just, it's visible? Okay. All right, so let's do this. So I'm just going to open the Python interface, which will allow us to see the files. Okay, so this is how the interface looks. All right. And there are different possibilities. If you want to create an input file, a new input file, you can generate a new input file. If you want to have already an existing input file, you can import an input file, and you can also do post-processing. So let's do this in the want of time. So you can, once you import a new input file, you can essentially choose different models. So this is an update from the previous solver that we had. We had the Grand Potential, KKS GPU CUDA, KKS GPU OpenCL, and Khan Hilliard. So two new additions have come into this interface. The solvers were existing, but you have entered the interface, which is now the OpenFOAM and the AMREX, which were part of the Multiphysics solver libraries, but now they have become part of this interface as well. Okay. So you can then choose an infile. I will just go there and choose an infile. And for example, I will choose maybe this. And it says that something is missing. So essentially, you can You can go there, and what it does is it populates all of these fields that are necessary for running the simulation from the infile that it just read. All right, so there are details that are related to the simulation geometry, discretization, space and time, and all of that, which can be imported over here. Then you have information about the phases. So you have number of phases, number of components. So this is a multiphase. The solver I have selected is a multi-phase, multi-component solver, which means you can choose a number of phases and a number of components. And depending on the number of phases as read from the infile, it gets populated over here. It gives some names to these files from the infile that it is read. But these are proxy names. You can choose any name that you want to have. And that's the same with the number of components that you choose from. Okay. Similarly, you can go ahead and choose, tell how many time steps you want to do, what is the smoothing steps, and the just tell me whether this is more easily visible or the other one. This is easier? Other one? Okay. Because the font gets smaller, so I was wondering whether this is easier, is it? Okay. So this is essentially a number of time steps you want to run, whether you want to restart your simulation, how many preconditioning steps do you want to run, and all of that. And then you went to essentially the properties, where the material properties enter relevant to the phases that you are entering. So you have the two phases in the system in this particular case, and you can essentially choose different constants, the interfacial energies, the functional properties, which means which thermodynamic description that you want to choose, and phase compositions that are relevant for the thermodynamic description that you have chosen. Then you have boundary conditions, and you can choose each field and associate each boundary condition to this field. So you can choose different boundary conditions. In this particular case, we are using PVC. So we'll use PVC, and you can just essentially go to each boundary and choose which boundary condition you want to choose, right? So you see this red line, red thing lighting up over here, essentially the relevant boundary and what boundary condition you want to prescribe at that boundary for that particular field, right? And then you can do something nice. You can do filling. So for filling, you essentially have options with respect to different shapes. So if you choose for 2D, a relevant shape is a cylinder. So you can actually have a cylinder, and you can choose a starting point and a radius to start with, and get starting with the simulation. And you can also import a shape. Let's say you have a file containing the shapes. You can actually start with that as well. But in if you want to something, add a new shape, you can just add over here. And what you can do is also to add several of them. You can keep adding cylinders, or keep adding different shapes into the domain, and they'll keep filling in the domain as and when it goes. And if you want to change something, you can go back and even edit the shape. So then you go to the model specific parameters, and these are again with respect to that particular model, what you want to run. I'll keep it simple here and go over here. So these are specific. You can actually go to each of them, and if you click, you should be able to see the what these parameters are all about. And then you come to the stage where you actually just generate this. I will just say P1. You have to give file names to this thing, to the things that you have created over here, and choose a directory where you want to store it. So it will store the data. And then you choose an output file, and you can then launch the simulation. So it will do some stuff, and you essentially can start off seeing the simulation, which will just start off, right? And I've given some brief time for the simulation, so it will do this. So after this is done, you can essentially close this window, and you can preview these things in ParaView, and also go to the MicroSim tool and post-process the data, where there are a host of post-processing tools. So in one of the sessions, you will get a brief description of what this thing is all about. Okay. So you can have different tools that you can utilize for how the simulation ran and so on. Okay, so that's the thing. So the new things over here, I will describe by going back to the presentation. So before we do that, just for record these. The place where our repo is placed is over here. Our website is here. I mean, they are now same, so you can essentially, it's hosted over here, so you can directly type microsim.co.in and you will get all the relevant updates that are happening in our software. And we have a YouTube channel where all the videos we are developing in this particular workshops will be uploaded for reference for future users who want to get on to using this software. So some brief simulation examples that MicroSim can be utilized for. So we can do single phase dendritic solidification, the classic utilization of the solidification method. You can carry it on to multiphase solidification, where we have different phases with different orientations, and you can have any number that you want to have. Then you can do precipitation reactions of this type in 2D and 3D. So on the left is a 2D simulation. On the right is a simulation where you have a comparison between precipitate coarsening that is having isotropic energies without elasticity, and on the right you have a situation where you have elasticity playing a role. So one of the things that our solvers are capable of is, particularly the MPI solvers, is that they scale very well. So just for showing you briefly, the left on the simulation is performed with 4 million points, and on the right is a 16 million points. And the left simulation was launched with 4761 CPUs on the Parampara Vega machine, and on the right the same size, same type of simulation, but 16 times 4 times larger. We utilize four times the number of CPUs, and you can get the same number of iterations done in the same time, which essentially shows that the system is essentially scaling, and you can use large number of CPUs for these calculations. Now this become relevant when you want to launch very large systems, relevant for material science problems. So material science problems are typically HPC problems because the microstructures are typically not as simple as this, but they will be complicated, and there you require a large simulation boxes and smaller grid resolutions to resolve, and thereby you need to be able to launch them with a large number of CPUs. So also we have GPU implementations which are OpenCL and CUDA based. So these solvers are being developed at IIT Madras, IIT Bombay, and as well as IIT Hyderabad, where you have, as well as AMRICS at CDAT Pune, where you can utilize GPU implementations for achieving the same problem. So that gives you flexibility, as I was talking about, for launching solvers with different hardware. As I said, we have one of the USPs of our thing is that we are able to couple with thermodynamic databases. So this is a real system, which is an aluminum zinc alloy, where you are having dendritic evolution, but dendritic evolution in aluminum zinc system, and the same thing you can do, as I said, in a multi-phase setting with multiple phases involved. Okay. This is a part of our multiphysics solver, which is capturing a typical industrial problem where you are essentially doing casting. So in casting, the typical situation is that you start off with an alloy, you have some nucleation happening, and then there's a cooling procedure by which the system cools and the microstructure evolves. So this has been incorporated into our phase field module in the open form module that is existing, where essentially you see over here you have a multiple dendrites growing with multiple orientations, and as the system is evolving to this microstructure, you actually can extract a cooling curve, which is the temperature versus time curve, as well as the segregation, that is the liquid concentration in the domain, as a function of the fraction solid. Now, why are these important metallurgically? The average liquid concentration in the domain will influence the post-solidification phase transformations and the heat treatment that you would like to give. So it is an important information for any metallurgical industry. Similarly, the temperature history itself is important for the metallurgical industry because you want to again predict what phase transformations are going on during this. So this is a larger scale simulation of the same thing, where this is now launched on a size which is about 36 million points. And this was done again on the Parampraveda, and essentially shows you that you can do very large simulations, much relevant for the materials problem at hand. So this is something about our microstructure, about the post-processing tool. As I said, we can extract information from the evolution of the microstructure, and this is, as you see, there is a coarsening simulation that is going on, and as the coarsening simulation is going on, you see the precipitate count is getting calculated, and you can calculate different metrics. This is just a precipitate count, but you can essentially measure size of the precipitates. You can also measure phase fractions, surface energy, and all of that from these tools. So this has become, and all of this data can also be exported into CSV files for further processing, which makes it even more useful for anybody using it in the academia as well as in the industry. So I'll go to now some of the updates that have happened in the last year. And one of the principal updates has been the incorporation of elasticity in all modules. So this is, for example, a coarsening simulation that is happening in the NIAL-MO ternary system with the incorporation of a cubic elastic stress, cubic elastic coherency stress. And what you see is that you are going into growth and then followed by coarsening, where the precipitates, some of them are growing and then the smaller ones are disappearing in the coarsening regime. So this is something now that you can do in almost all the solvers that are updated in the repository now. That means you can include coherency into the modules, coherency stresses. Similarly, you can do now couple it with coherency stresses, but with multi-phase, and this is again relevant in the metallurgical standpoint, because typically in most metallurgical systems, when you have precipitations, you will also have variants. You will have different 2 or 3 variants of the precipitates that emerge from the precipitation reaction. So this is, for example, 2 variants that emerge, and these are tetragonally associated. So essentially, you have one laterally elongating and one vertically elongating in this reference frame, and while they're elongating, you're essentially capturing how they coarsen during the microstructure evolution. So I will let this guy complete. Similarly, you can go and make it even more complicated. You can run. Now you have 3 phases that are 3 variants. So you have 2 tetragonal variants over here. The ones that we saw last time, one elongating like this and the other elongating like this. But we have a 3rd variant, which is the blue variant over here, which is a dilatational variant, which means you have just dilatational coherency stresses, which means it will remain cubic in the equilibrium shape. And while these 3 variants emerge from the microstructure, because of the coherency stresses are non-local in nature. So when that exists, you have evolution of the microstructure, which inherently involves organization of the microstructure during the coarsening process, which is evident from how the precipitate evolution is happening in this system. So by the way, so some of these shapes are already reported in literature and experiments. So that essentially was one of the motivation to do such a simulation to actually make a comparison to what is there in experimental literature. And then you can essentially take it even more complicated and include the case of self-accommodating variants, where essentially the sum of the eigenstrains of these variants will add up to 0, and you can include any number of variants over here, a number of phases, including translation variants, for example, giving you more interesting structure formation in the presence of elastic stresses. This makes it now very powerful, because now the software can do therefore both solidification problems and then the corresponding the precipitation reactions, which would happen during the post-processing of the material during heat treatment and homogenization. So then the entire process chain that is typically relevant for a metallurgical industry becomes accessible to your to the software. Next type of problems are essentially grain growth problems, which are also relevant in industry. So this is again a simulation of grain growth happening. I will just speed it up a little bit in the interest of time. So you can essentially see grain growth happening as the simulation is progressing, and you can do this in 2D and 3D, and just for representation purpose. All right. So grain growth is also a new feature that has been added in most of the solver modules that you have in the repository now. And third, last, in terms of solver modifications, all of the solver modifications are now 3D compatible. That means you can do both 2D and 3D computations. So this is a representative simulation of dendritic solidification, but you also do have 3D precipitate evolutions over here. So all solver modules are 3D compatible, allowing you, again, in terms of realistic microstructures, you can now simulate them. An addition that has happened to the OpenFOAM modules is that previously in the orientation field models that was present in the older release, you could do only 2D multi-grain solidification or precipitation, but now you can do 3D 3D multi-orientation precipitation as well. But this required that you can represent, you needed to represent orientation in a 3D space. So we chose the typical route that is taken in the phase field literature, which is the quaternion based approach, where you have 4 components representing the orientation in the space, which allows you to essentially make rotations in a very simplistic algebraic manner, reducing cost, and therefore you can model. Again, this is the aluminum zinc solidification in a multi-grain setup, so you can see the orientations over here in 3D using that quaternion based approach. So you'll see a more elaborate discussion about this in the OpenFOAM session that we are going to see. Now, features that were added in post-processing, this relate to what you can compute out of your microstructures. So one of the things that were possible to do is which you saw a brief intro of, is that you can compute the triple points, the positions of them, the number, and the coordinates of the triple points as the microstructure evolves. So these yellow dots that you see in the microstructure over here, these correspond to the triple points in the microstructure, and you can essentially track them. So this is a POTS model while it is evolving, and you're essentially tracking the triple points. You can do the same with phase field type grain growth, and you can do the same of tracking the triple points. Why are they important? Again, tracking the triple points can be utilized for reduced order models for grain growth, where you can essentially map the positions of the vertices of these triple points and write down these models. So that makes it one of the useful applications of such tools. And you can do quadruple junction calculations as well. So this is a 3D microstructure, and these dots that you see over here, it's very faintly visible, but these dots that you see are the positions of the quadruple points in the junction, because in 3D, quadruple points become relevant in addition to the triple lines. So triple lines also can be derived, but you can also get the quadruple points out of your simulation. So these are features added in the post-processing module. This is one of the features I like the best, and which is something that is relevant for any through process modeling that you would like to do. So I will give a brief demonstration how this works, and I have named it sequential multiscaling in the context that you do a solidification simulation and you extract a part of the microstructure for post-processing. That means you would like to know how would that particular microstructure evolve during a subsequent processing, for example, heat treatment. All right. So what you would need to do is to take a relevant part of the microstructure out from a solidification microstructure and do the corresponding lower length scale simulation, and therefore I have referred to as sequential multiscaling. So for this, essentially, we let's say this is a microstructure that is derived out of a solidification of a droplet, where you have dendritic microstructure in a droplet. This is something that is relevant for atomization problems, where you have solidification evolving there. But now I want to extract a little bit of this microstructure. So we have a tool over here, which is it's called resolution interpolation (VTK), and what it does, it essentially breaks up the domain into smaller parts, and you can keep recursively choosing smaller and smaller parts of the domain until you reach the desired position in the domain that you want to simulate further. So here we are going recursively into smaller and smaller parts of the domain, and essentially taking out the composition fields that will be relevant for the post-processing that you would like to conduct. So here, as you see, we have gone down to a stage where it's almost uniform composition. It is not entirely necessary that you go to a stage where it's entirely uniform. You can go to a stage where there is non-uniformity in the composition existing, but this is just for reference purpose, where the resolution has been brought down and the part of the microstructure has been extracted, which is of relevance. So once you have done, it will essentially calculate the average compositions in this domain, in the domain that you have extracted, and these average compositions are then utilized for constructing the thermodynamic files from the that are required for the phase field purpose. And this is again interaction with TC API or PAN API for extracting the information. So you use the local composition there to extract this information and then construct an infile of this type for running the subsequent simulation that you would like to conduct. Okay, so so for example, this is a precipitant simulation or in that domain that you extracted using the thermodynamic information that you extracted. Now, why is it important? Because you see there is a non-uniformity of composition in this microstructure. So the precipitate evolution that happens at the center core of the dendrite and at the tip of the dendrite will be typically different. So you would like to map that particular difference in your microstructures, and that's where this particular tool becomes important. So this is, for example, a microstructure evolution of the precipitation reaction at the dendrite center, and the same is happening at the dendrite tip. And there are observable differences which are not picked up visually, but when you, for example, this is much coarser than this is much finer. Now, these differences are important to capture in the sense that during after post solidification, if you were to do a homogenization treatment, the starting microstructure itself might be of interest, because this inhomogeneity might stay beyond the post heat treatment and homogenization stage. So then it becomes relevant to capture this for any property assessment that you would like to have. Okay, so just summarizing the updates from the previous version. So we have all solvers which are three-dimensional now, that means 2 and 3. You have MPI, OpenFOAM, CUDA, and OpenCell based solvers which have now all elasticity modules. The grain growth modules are existing, have been added to the grand potential MPI solvers. AMREX solvers are capable of accessing both GPUs and CPUs, are now capable of multi-phase certification. So this is one of the newer additions, because the AMREX environment gives us the flexibility that the same code actually runs on both CPU and GPU with minor modifications in the script. Then, as I have just displayed, highlighted, that the post-processing tools now have quadruple and triple jumps and triple line identification capabilities, which maximize the its applicability. And then we have added this sequential multiscaling tool, which I think is relevant for which is going to be relevant for through process modeling that we want to utilize this software for. And finally, we have singularity images for installation. We have, in the last year, we have had several requests and interaction with people who have tried to utilize our software. And one of the key challenges has been the installation part, because there are a lot of dependencies that need to be installed together. So what we have come up with are singularity images now, which essentially package all the dependencies into a Docker or a container, which essentially can be docked into your machine, and the installation becomes self-contained using that singularity image. So this is something that you will see in the session that is following the present one, where you will see demonstration of the singularity images. You will be getting singularity images for installation on your computers, which simplifies the transfer of the software to people. I mean, it becomes relevant also for people who are in industry, who are constrained by internet usage, so they cannot install all the dependencies through connection to the internet directly. So these singularity images will be useful for that sort of activity as well. So with that, I think I will again acknowledge the team of developers and the past PhD students and master students on whose work I insist that this has been possible. These developments have been possible. So I thank all of them. And then I will be open to any questions that I might have. Yeah. So let's go to the Teams thing, because I think there might be some hands. Okay. Yeah, that is one
Hello,
question.
Abhik. Good morning.
Hello.
Hi, good morning.
Shashuto. Yeah, tell me.
Ah, so
No,
that
we miss you.
singularity images.
So we are
Ah,
missing you here.
yeah, anyway. So the
Uh,
singularity images are now packed with the latest version of MicroSim.
yeah. So they will be packed on. So they are going to be given to the people now for installation purposes. So they'll have a
Okay.
live demonstration of that today. Yes.
I think it is a very good addition because without
Right.
singularity,
Right.
it was really difficult for industries.
Right. Absolutely. I think that is something we realized, and I think we have
Yeah, there are
implemented.
questions here. There are questions.
Shupru is there. Okay. Hi, Shupru.
Hi, how are you?
I'm doing good. I'm doing good. How about you?
Yeah, good. Yeah, so uh, yeah, I was like curious about so are you planning to expand the capability on maybe
Uh,
recrystallization simulation for industry or also fracture simulation with
Yes, so
this?
we will have editions of recrystallization very soon. This is something that is planned. So recrystallization is a version of it already exists. It's not going released as yet, but we have a thermodynamic description which can interact with stressors and therefore model recrystallization. So it will be released mid this year or next year. So we will have it. Fracture is something might take a little bit more time, but the essential pieces of fracture have now entered some parts of the grand potential solvers, MPI based, because you use the same iteration technique that you utilize for solving the fracture problem. So in some sense, parts of it again is existing. So we will have the fracture module, but may not be in the near feasibility. We will have it, but we'll have it soon.
Yeah, in
Okay.
fracture, I just wanted to understand from Supriyo. In fracture, are you talking about the infinite elastic contrast?
Yeah, he is, I
Uh,
think, talking about that only. That's the, I mean, vacuum and this one, air and.
Means
yes.
okay.
I mean,
So
one
yes,
has to
that
solve
part.
the class. I mean, yeah, one has to solve the classical wave equation along with the phase field for the damage evolution, and couple them in the way that typically is done in literature, and you would have the fracture evolution. There might be some theoretical developments necessary for ductile fracture. For but brittle fracture, one could ideally do. So whatever is the state of the art, we'll try to have it. But again, as I said, it might not happen in near vicinity, but it will certainly happen possibly in the next 1 and 1.5 years. So
Means one can
Yeah.
do it. No,
yeah,
means basically it's already capability is there,
yeah, we have
and
to. Yeah,
even on the N50 side also the capability is there.
right.
However, yeah, it will happen in the near future, right?
Yeah.
Okay.
Yes. Other questions? Questions from the audience here? Questions? Yes.
Right now, can it capture any deformation effect or texture development, or in the future will it?
So recrystallization, as I said, is going to be part of the future development. It's going to happen soon. So where we will be able to a little bit of uh, predict the texture of the material in response to the deformation. So what will be as an input to the model would be the stress field that emerges out of the deformation, and using that input, the decrystallization would be essentially modeled. Right?
Hello.
Yes.
Yeah, good morning, sir. Sir, this is
Yes.
Manish Sinha. Actually,
Ah,
I
Manish.
wanted
Hi.
to
Hi.
know,
Hi.
hi, sir. So I wanted to know basically, does this how to download and install this software, because I'm facing
Yeah,
the
so-
trouble in downloading and installing this software.
So Manish,
And-
you will
yeah.
get a demonstration of that today. So my team will essentially share a Singularity image link that you can download at your place. The people who have attended live will get that as a live thing in a USB. So they will be utilizing that. But for people online, you will get the link through the Teams thing itself, where you can where it will essentially utilizing that link. Once you click on the link, it will download whatever is needed in that Singularity image, and then it will essentially uh, get started. So that is going to simplify your installation problem, is what our impression is, because everything that is required and is required for the software has been packaged in one container, and so nothing outside of that will be needed, and that will be sort of forming an environment on your computer. So that I think is the easiest way to do it. So you will get a demonstration of that today during the installation.
Okay. So I will get the link, some link of.
Yes. You will get the link. Yes.
Okay. Thank you, sir.
So visitors from Pratt and Whitney, are they there here already? Are there? Any other industrial participants? Any from other industries? Yes. From where? Honeywell. Okay. Intech. Okay. Okay. So I think if there are no further questions, what we can do is we can just transition to the installation part of this workshop in this session, where my team will take over, and they will start off with the installation. So I'm looking for Swapnil. Swapnil. It was audible from outside, right? Yeah. So I think Swapnil will take over for the installation along with Pradeep. So they will get you along with the Singularity images. They might have already have some USB images available. Yeah. So they will share with the physical participants over here, and for the online ones, he will share a link which you can utilize for. So after this session, we will have a brief introduction into phase field, which will be provided by Professor Gururajan, so that you get some basic feel about what is the theory behind these phase transformations and what is the theory behind these evolution equations which are coded in the solver. So that brief introduction is necessary for appreciating some of the stuff that you will be seeing in the post sessions, which will be solver modules essentially.